This is a really brief discussion on metallic bonding and why metallic bonding permits conductivity. So if you can imagine that a metal, if we could zoom in on a metal and we could see the atoms in the metal, what we would see is that there's organization. And when we say organization in chemistry, we mean something like this, that there's a pattern in the atoms. And of course, this wouldn't be the pattern we would see if we actually looked at a piece of metal, because it would be three-dimensional and every metal can be different. But nonetheless, the idea is there. And on a large scale, you can't see this in metals. And crystals, you could see it. And there can be a lot of disorder in this structure, and you'd still get the same metallic characteristics. But nonetheless, there's a propensity for metals to order. What I've drawn here, these dots, would represent a nucleus. And so each one of those dots has a positive charge. The example we used in class was zinc, and if it was zinc, then each one of those dots would represent 30 protons and some number of neutrons. But of course, we also have to count for the electrons. And if we had a piece of metal, a piece of zinc metal, we can touch it. That means it's neutral. Anything that had any significant amount of charge would shock us if we touched it. And here, these pieces of metal on their own certainly don't shock us. And so for each of these 30 protons, we need 30 electrons. And it is true that most of the electrons would be concentrated around each atom. And you could keep doing that and it would take forever. But the idea is that each one of these atoms has a certain number of electrons that stay really close to it. And we call those localized electrons. The electrons that are stuck to this nucleus stay at that nucleus. But there are some electrons that move freely amongst all of the nuclei. They can roam around, and this is often called the sea of electrons. It's just moving, and so electrons are shared, and that's what we mean by metallic bonding. It's not like this atom is bound to that atom like we would see in covalent bonding. No, that's not true. The electrons are shared over a much larger region of space, resulting in the metals being bound together. And there's a lot of properties that rise out of that. One of those properties is that if we put electrons in on this side, and I'll use the limit. I've only drawn a few atoms here, so I'm going to use the limit of drawing one electron going in on one side of this structure, then we get an electron out on the other side. So we could say that the metal just conducted an electron, and that would be a proper use of the word to conduct. And, of course, then I might have this idea that if I had a whole lot of electrons on one side of a room, and I wanted to move all those electrons to the other side of the room, I could do that with a piece of metal that is large enough. And it turns out that absolutely does work. You can move a lot of electrons that way. And if we move a lot of electrons that way, we would call that electricity. And so clearly metals are very good at this. We run electricity vast distances. The power plants that power our towns are often well out of sight of the town. A lot of people don't even know where they are. And so this is just kind of a brief description of why metals conduct electricity. Of course, this can be massively complicated, as all things. There's a lot of mathematical stuff you can do. We'll put it that way. And then, you know, and all metals don't behave exactly the same, but they all, to be a metal, have to have this basic characteristic that they have a sea of electrons, and that's why if you put one electron in one end, an electron pops out the other.